2 days from now, in the early morning darkness of Sunday, August 2nd, a cloud weighing roughly 1 billion tons is scheduled to arrive at this planet. It left the Sun on Thursday, launched by a flare so modest that most of the world never noticed. An M1.9, a number that should have meant nothing. But the flare refused to stop erupting. It burned for hours, lifted an enormous cloud off the Sun and aimed it our way, and now forecasters are calling for a moderate geomagnetic storm with auroras that could reach New York, Wisconsin and Washington state. Yet the single number that decides whether Sunday stays moderate or becomes something far bigger is sealed inside that cloud, and nothing on Earth can read it until about an hour before impact. If this has you hooked, subscribe to the Sky Lab and tap the like button, because we track every eruption and every arrival as it happens. Drop a comment telling me where you're watching from and whether you've ever seen the aurora with your own eyes. Now let's get into it. Part 1. The explosion that wouldn't stop. At 1700, Universal Time on July 30th, 2026, a patch of the Sun's surface labelled Active Region 4492 reached the peak of a solar flare. If you'd been watching the official classification feed at that moment, you would have shrugged. The flare registered as an M1.9. On the scale forecasters use, that is a medium-sized event, sitting near the bottom of the medium band, roughly 1/10 the peak output of the flares that make international news. The Sun produces flares like this all the time. Most of them are footnotes. This one was not a footnote, and the reason it was not a footnote has almost nothing to do with that number, and everything to do with what the number failed to capture. A word on the name, since this region will be with us all video and likely all week. Sunspot groups are numbered in sequence as they are identified, a ledger kept continuously for decades, and the count recently rolled through its 4,000th entry of the current numbering era. 4492 is simply the 4,492nd entry in that ledger, an accounting label with no drama in it. The drama is in the region's behaviour, and its behaviour this week earned it a place in a much shorter list. The handful of regions each year whose eruptions come with an arrival date attached. Because the flare did not stop. A typical impulsive flare rises, peaks and collapses back to baseline in a matter of minutes. It is a spike, a camera flash, a snap of magnetic energy released and spent. What happened at Active Region 4492 on July 30th behaved differently. The X-ray output climbed to that modest peak and then simply refused to come down. It held, it smouldered. The eruption stretched on for hours, releasing energy continuously across a window so long that forecasters place it in a special category, the long-duration event. And while the peak never looked impressive, the total energy released across all those hours added up to something far larger than the classification suggested. Here is what that sustained release actually did. As the flare burned on, an enormous filament of solar material, a rope of relatively cool, dense plasma that had been suspended above the Sun's surface by magnetic fields, tore loose and lifted away. The prolonged eruption gave it time to rise, time to accelerate, time to drag an immense cloud of magnetized plasma up out of the Sun's atmosphere and hurl it into space. That cloud is called a coronal mass ejection, and this one is big. Big enough that within 6 hours of the flare's peak, a brand new instrument on an American weather satellite watched it balloon outward from the Sun as a vast glowing halo. And it is coming in our direction. That is the reason this video exists, and it is the thread that runs through every single thing you're about to hear. A modest flare with an unusual amount of patience lifted a storm off the Sun on Thursday, and that storm is now crossing the 93 million miles between the Sun and this planet. The models say it arrives on Sunday, August 2nd. The forecast says the encounter will be a glancing blow, not a direct hit, strong enough to spark what the National Oceanic and Atmospheric Administration classifies as a G1 to G2 geomagnetic storm, with the peak expected in the early morning hours of Universal Time, around 6 to 9. If that G2 level verifies, the aurora, the northern lights, could push far enough south to be visible from New York, from Wisconsin, from Washington state. So the promise of the title is real, and you now have it. The Sun erupted again. It is coming for Earth. It arrives Sunday. What the rest of this video is about is everything hiding inside that simple summary, because almost nothing about this event is as simple as it sounds. Take a moment with the scale of the object in transit, because words like cloud undersell it badly. A typical coronal mass ejection carries somewhere in the range of 1 billion tons of solar material, plasma hot enough that its atoms have been stripped of electrons, threaded through with a magnetic field torn loose from the star that made it. By the time such a cloud reaches Earth's distance, it has commonly expanded to tens of millions of kilometers across, a structure so much larger than our planet that the encounter is less a collision than an engulfment. Earth does not get hit by these things the way a target gets hit by a projectile. Earth gets swallowed by them, wrapped for hours inside a piece of the sun's atmosphere that came loose, while our magnetic field fights a running negotiation with the field embedded in the cloud. That negotiation, and nothing else, is what the word geomagnetic storm actually describes. Start with the eruption itself. Solar flares and coronal mass ejections are related but distinct things, and the difference matters enormously for what happens this weekend. A flare is electromagnetic radiation, light across the spectrum from radio waves to X-rays, produced when magnetic field lines above a sunspot group snap and reconnect into a lower energy configuration. That radiation travels at the speed of light and reaches Earth in 8 minutes and 20 seconds. Whatever a flare was going to do to us, it did on Thursday afternoon, before anyone had finished reading the alert. A coronal mass ejection is different. It is matter. Billions of tons of plasma, threaded through with the sun's magnetic field, physically thrown off the star and sent ploughing through the solar wind. It does not travel at the speed of light. It travels at hundreds or thousands of kilometers per second, which means the journey takes days, which means we are right now in the strange in-between time. The eruption already happened. The consequence has not arrived yet. It helps to know what kind of place this cloud came from. An active region is the technical name for a sunspot group, a patch of the solar surface where concentrated magnetic field punches up from the interior and chokes off the normal boiling convection of hot gas. The choked patches run cooler than their surroundings, and cooler means darker, which is why sunspots look like blemishes on the disk. But the darkness is a disguise. Those spots mark the footpoints of enormous arcades of magnetic field arching through the atmosphere above, loops carrying stresses that build for days or weeks as the sun's rotation and churning interior twist them like elastic bands. Every flare is the moment some of that stored twist lets go. Active region 4492 had been carrying enough stress to burn for hours, which tells you the reservoir it drew on was far larger than any single snap of field could spend. The filament deserves its own portrait too, because the filament is the part that physically left. Filaments are among the strangest structures the sun builds, channels of plasma 100 times cooler and denser than the corona around them, levitated above the surface for days or weeks by a magnetic hammock. Seen against the bright disk, they appear as dark, snaking threads, some stretching hundreds of thousands of kilometers, longer than the distance from the Earth to the Moon. They are storms in suspended animation. As long as the magnetic hammock holds, a filament simply hangs there. When the field beneath it destabilizes, the hammock tears, and the entire channel, all those billions of tons of suspended material, is released upward at once, the core of the coronal mass ejection that follows. That is what the long flare of July 30th did. It did not just flash. It cut down a structure the sun had spent days assembling and threw it at the inner solar system. Reconstruct Thursday afternoon as a timeline, and the sequence is almost cinematic. 1700 Universal Time, the X-ray peak. The moment the classification feed stamped its misleading M1.9. The flare refuses to decay, output holding hour after hour as the filament climbs. 1845, Universal Time, less than 2 hours after the peak. Radiation detectors at Earth register the first wave of accelerated protons arriving from the blast, the earliest physical touch of the event on our neighborhood. 2055 Universal Time, that particle flux reaches its first crest. 2300 Universal Time, the new coronagraph delivers its verdict frame, the halo, the picture that turned a curiosity into a countdown. One afternoon, one modest number, and by midnight the entire space weather apparatus of the United States was oriented towards Sunday. That in-between time is where forecasting lives, and forecasters spent Thursday night doing what they always do when a halo appears in a coronagraph, measuring, modelling, and arguing about speed. We will get to their numbers and to the genuinely strange fact that this eruption produced two very different speed estimates at once, because that disagreement is not a technicality. It decides when the cloud gets here and how hard it hits. But before any of that, sit with the central oddity one more time, because it is the engine of this entire story. The sun produces the flares we grade as terrifying, the X-class monsters, several times a year. It produced one at the start of this month. None of those was followed by a watch like this one. Instead, the eruption that earned a multi-agency storm watch, the one now crossing interplanetary space with a proton storm running ahead of it, came from a flare most casual observers would have dismissed entirely, and a MEM 1.9, a number that lies. Why does the number lie? What is it about a slow, patient explosion that moves more material than a fast, violent one? The answer sits at the heart of how the sun actually works, and it has embarrassed forecasters before, most recently 3 years ago, when a flare almost exactly this size produced a storm that ran 2 full levels above its official watch and lit the sky up over half of the United States. We will open that case file shortly. First, we need to talk about the shockwave, because the shockwave is how we know this cloud means business. Part 2. The shockwave with 2 speeds. Something ran ahead of the eruption on Thursday, and it announced itself on radio. As the coronal mass ejection accelerated away from active region 4492, radio telescopes monitoring the sun picked up a distinctive signature, a slow, sweeping whistle descending through the frequencies, the kind of emission astronomers classify as a Type 2 radio burst. To a solar physicist, that sound means one specific thing. A shockwave is moving through the sun's outer atmosphere. Here is the mechanism, step by step, because it is worth understanding properly. The corona, the sun's outer atmosphere, is a plasma, a gas of charged particles, and every plasma has a natural frequency at which its electrons oscillate. That frequency depends on density. Near the sun, where the plasma is dense, the frequency is high. Farther out, as the plasma thins, the frequency drops. When a disturbance moves through the corona faster than the local speed of information in that plasma, it drives a shock front exactly the way a supersonic jet drives a sonic boom in air. The shock energizes electrons. The electrons make the local plasma ring at its natural frequency, and that ringing escapes as radio waves. As the shock climbs outward into thinner and thinner plasma, the emitted frequency slides steadily downward. Point a radio telescope at the sun during an eruption, and you hear the descent in real time, a falling tone that is, quite literally, the sound of a shock wave climbing out of a star. The speed of that falling tone tells you the speed of the shock, and this is where Thursday's event handed forecasters a puzzle instead of an answer. The Type 2 signatures from this eruption produced 2 speed estimates. One came in at 853 km per second, the other came in at 1,681 km per second. Those are not error bars on a single number, they are 2 different answers, and one is essentially double the other. Remember what this shock is attached to. This is the leading edge of the same storm the whole video is counting down, the one due here Sunday morning, so a factor of 2 in its speed is not an academic dispute. It is the difference between a cloud that crosses the Sun-Earth gap in about 2 days and one that could do it in barely more than 1. How can the same shock produce 2 speeds? Because converting a falling radio tone into kilometers per second requires an assumption. The math needs a model of how density decreases with height in the corona, and the corona does not publish its density profile. Physicists use standard models, built from decades of eclipse observations and spacecraft measurements, but the real corona above any particular active region on any particular day can be denser or thinner than the standard model assumes. Feed the same frequency drift through 2 different density assumptions and you get 2 different speeds. There is also the question of geometry. A shock is not a point. It is a vast curved front, and the radio emission can come from its fast-moving nose or from its slower flanks. Depending on which part of the front dominated the emission at which moment, the derived speed shifts. The listening posts behind these measurements are their own quiet global infrastructure. Dedicated solar radio observatories on several continents sweep the relevant frequency bands continuously, their spectrographs painting every burst as a bright descending stripe on a frequency versus time chart, and analysts read those charts the way meteorologists read radar. The craft is old. radio astronomy itself was partly born from wartime engineers discovering the sun jamming their equipment. But the discipline it feeds is thoroughly modern. Within hours of Thursday's eruption, burst lists and drift measurements from independent stations were being compared, which is precisely how the community ended up with two defensible speeds instead of one comfortable illusion. So the honest reading of 853 versus 1681 is not that one instrument failed. It is that the eruption was complex, the shock was extended, and the corona above active region 492 was not obligated to match anyone's textbook. The disagreement is real information. It tells us the uncertainty in this storm's arrival time is genuine, physical, and irreducible from the ground. Run the arithmetic yourself, because it frames the whole weekend. The sun sits about 150 million kilometers away. A cloud holding a steady 850 kilometers per second covers that distance in roughly 2 days. A cloud holding 1,700 kilometers per second does it in just over 1 day. The official forecast, arrival early on Sunday, August 2nd, lands about 2.2 days after the Thursday afternoon launch, which tells you something about how the modelers weighed the evidence. They are betting on the slower end, or they are betting that whatever initial speed the cloud had, it will not keep it. That second bet is usually the safe one, and the reason is drag. A coronal mass ejection does not fly through empty space. It plows through the solar wind, the continuous outflow of particles the sun exhales in every direction, and the interaction works like air resistance in reverse of whatever you need it to be. A CME moving faster than the ambient wind gets dragged backward and decelerates. A slow CME can actually be carried along and sped up. Fast eruptions launched at 2,000 or 3,000 kilometers per second routinely arrive, at Earth having lost a third or half of their speed. The wind tax is real, and every forecast has to pay it. The drag mechanism rewards a closer look because it behaves less like air resistance and more like traffic. The solar wind ahead of a fast CME cannot simply part and let it through. The cloud sweeps that wind up, compressing it into a dense, hot sheath riding just behind the shock front, a snowplow packing snow against its blade. Every ton of ambient wind the cloud sweeps up is a ton of material it must now carry, and momentum spread across more mass means less speed. The faster the cloud and the denser the wind ahead of it, the harsher the tax. This is why the giant historical eruptions, the ones launched at extraordinary speeds, still typically took well over a day to arrive, rather than the sprint their launch speeds implied. It is also why forecasters care so much about what the wind ahead of an eruption has been doing. A path recently swept clean by an earlier eruption offers less material to plough, less tax, a faster transit. And it happens that the week before this eruption, the sun was sending other material earthward. Storm watches were in effect for days at the end of July for earlier, separate ejecta. Whether those earlier events left the highway ahead of Sunday's cloud emptier than the models assume is one of the honest unknowns in the arrival forecast. One more distinction sharpens the picture of what the radio antennas heard. Solar radio bursts come in types, and the two that matter here bracket the event's anatomy. Type 3 bursts are fast whistles, frequencies falling in seconds, produced by beams of electrons fired along open field lines at a healthy fraction of the speed of light. They are the signature of the flare itself, the flash. Type 2 bursts, the kind Thursday's eruption produced, drift downward over minutes, not seconds, because they track a massive shock climbing outward at mere hundreds or thousands of kilometers per second. Electron beams are weightless messengers. Shocks are freight. When the record shows a long, slow Type 2 descent, it is documenting that something with enormous inertia was physically forcing its way out through the corona, which is precisely the thing a modest flare classification would never tell you was happening. And this particular cloud is flying into an unusually quiet ocean. The solar wind flowing past Earth right now is creeping along at about 302 kilometers per second, close to the floor of what the sun ever produces. Hold that number. It matters twice, once for the physics of the crossing, and once, later, for a much stranger reason involving how eerily calm the space around this planet is at the exact moment something large is inbound. There is one more thing the shock told us, and it may be the most important. Shocks do not just make radio noise, they accelerate particles. Within 2 hours of the flare's peak on Thursday, detectors in orbit began counting fast protons arriving from the sun. The opening notes of a radiation storm that would cross an official alert threshold fade, and then, in a twist that tells its own story about what is happening in the space between here and the sun, cross it again. That double-tap radiation storm is running ahead of the cloud like an outrider, and we're going to give it the full treatment shortly. But first, we owe a debt to the machine that saw the eruption at all, because the picture that anchors this entire forecast, the image of a glowing ring swelling around a blacked-out sun, came from an instrument that has only recently taken up its post, and the story of why it exists is the story of how close civilization has been cutting its solar early warning system for the last 3 decades. Part 3. The new eye that caught it. The picture that started the countdown was taken at 2300 Universal Time on July 30th, 6 hours after the flare peaked, by a camera called CCOR-1, riding on a satellite called GOES-19, parked in orbit 35,000 kilometers above the Western Hemisphere. You already know GOES satellites, even if you have never heard the name. They are the geostationary weather sentinels of the United States, the source of essentially every satellite loop you have ever seen on a hurricane broadcast, hanging fixed over one longitude so they can stare at the same hemisphere without blinking. For half a century their job was to watch Earth's weather from above. The newest generation quietly took on a second job, watching the sun's weather from the same perch. GOES-19 carries X-ray sensors, the very instruments that grade flares, particle detectors that count the radiation storms we will meet shortly, and now, for the first time in the fleet's history, a coronagraph. The same platform that tracks a hurricane's eye wall can now track the eruption that might, 3 days later, paint aurora over that same hurricane's ocean. One satellite, both kinds of weather, which is fitting, because this channel has been arguing for years that they were never really separate subjects. The image shows the sun blacked out. That is deliberate, and it is the whole trick. CCOR-1 is a coronagraph, an instrument built around a simple, century-old idea. Put a disk in front of the star. The sun's surface is about 1 million times brighter than its outer atmosphere, so any camera that lets direct sunlight in sees nothing but glare. Block the disk and suddenly the corona appears, the ghostly outer atmosphere streaming and shimmering around the occulting spot, visible from Earth's neighbourhood at any hour instead of only during the fleeting minutes of a total eclipse. A coronagraph manufactures an eclipse on demand, continuously, forever. And in that manufactured eclipse on Thursday night, a bright structure bloomed, not a jet firing off to one side, a ring, a halo of light expanding outward around the blocked-out sun, brightening and swelling frame by frame. Understand what halo geometry means, because it is the single most consequential piece of information in this entire event. When a coronal mass ejection leaves the sun sideways, perpendicular to your line of sight, you see it in profile, a bubble arcing off the edge of the disk, photogenic and, for you, harmless. But when a CME comes straight at the camera, you do not see a bubble moving in any direction. You see it grow in every direction at once. The cloud expands as it approaches, and from dead center, it projects as a ring swelling around the sun, exactly the way headlights at night look like an expanding blur of brightness when the car is driving directly toward you. A halo does not tell you the cloud is beautiful. It tells you the cloud is aimed at you, or precisely away from you. And since active region 4492 was on the Earth-facing side of the sun on Thursday, the away option is off the table. That is the moment the eruption stopped being solar trivia and became a terrestrial forecast. The halo is why there is a watch. The halo is why this video has a countdown in it. One frame, one geometry lesson, and suddenly every space weather desk on the planet was doing arrival math for Sunday morning. It is worth pausing on the machine itself because the camera that caught this cloud represents a quiet changing of the guard. CCOR-1, the compact coronagraph, is the first coronagraph the United States has ever flown as an operational instrument, meaning an instrument whose day job is forecasting rather than research. It launched aboard GOES-19, the newest of the nation's geostationary weather satellites, and it took up its watch within the last couple of years. Before it, the entire Western world's ability to see a coronal mass ejection coming, the raw capability underpinning every CME warning issued for nearly 3 decades, depended overwhelmingly on a single research instrument. The LASCO coronagraph aboard the SOHO spacecraft launched in December of 1995. Let that arrangement register. SOHO was designed as a science mission with a nominal lifespan measured in a few years. It kept working and kept working and kept working, and because nothing operational existed to replace it, an aging research telescope from the Clinton administration quietly became load-bearing infrastructure for the electrical grids, airlines, and satellite fleets of the 21st century. Forecasters knew it. Agencies wrote reports about it. The single point of failure stayed single for almost 30 years, and the plan if SOHO died was, in effect, to squint at more distant data and hope. The arrival of an operational coronagraph on a modern weather satellite closes one of the longest-standing vulnerabilities in the entire space weather enterprise, and Thursday night's halo was exactly the kind of catch it was built for. Same-day detection from an instrument whose funding line and replacement schedule treats solar storm watching as what it has actually been for decades: weather forecasting for a civilization that lives inside a star's atmosphere. If you want a measure of how precarious the old arrangement really was, consider that the world nearly lost it once. In the summer of 1998, a sequence of ground control errors sent SOHO tumbling, its solar panels drifting out of the sunlight, its batteries dying, its instruments freezing in the dark 1,000,000 miles from any repair. For weeks, the spacecraft was silent and presumed lost. Engineers eventually found it with radar, coaxed power back cell by cell as its panels swung through sunlight, thawed frozen fuel lines, and against most expectations resurrected the entire observatory. Civilization's primary eye on incoming solar storms spent a season of that year dead in space, and its survival came down to improvisation and luck. That is the inheritance CCOR-1 retires. It also matters where the new eye feeds. A coronagraph frame is not a forecast, it is an input. When a halo appears, analysts fit the expanding cloud's outline across successive frames to estimate its true speed and direction, correcting as best they can for the cruel geometry that a cloud coming straight at the camera shows almost none of its real motion along the line of sight. Those fitted parameters, launch time, speed, width, direction, are handed to numerical models that simulate the inner solar system's plasma weather, the churning wind, the fast streams, the slow rivers, and inject the cloud into it, running the crossing forward in simulated time to produce the two numbers everyone downstream actually wants, when it arrives, and how hard. That modelling chain is where Sunday, August 2nd, 6 to 9 Universal Time came from. Every figure in this weekend's watch traces back through that pipeline to the halo frames a camera took on Thursday night. Picture the sequence as the frames accumulated through Thursday evening. In the first images after the eruption, a brightening bulge pushing past the edge of the occulting disk, ambiguous, could be a sideways event. Then, frame by frame, the bulge refusing to stay on one side, brightness creeping around the disk's rim, the structure widening its angular embrace of the sun, until the geometry became undeniable and the classification hardened from partial toward full halo. Each frame is a time-stamped measurement, and the expansion rate across frames is the raw material for the speed estimate that gets fed downstream. By the 2300 Universal Time frame, the one released publicly, the ring was unmistakable, and the analysts' overnight work was already defined for them. There is a particular quality to watching those sequences, even for professionals who have seen hundreds. The knowledge that the expanding ring is not spreading across the sky, but along your own line of sight, that the geometry of the image is the geometry of approach, is the closest astronomy comes to the view down the barrel. The halo image did one more job. Analysts classify these events by how completely the ring wraps around the occulting disk, and this one registered as a partial to full halo, wide, bright, and structured. Brightness in a coronagraph image is scattered sunlight, and more scattering means more material along the line of sight. This was not a wisp. The camera was watching a massive object leave, an object whose departure the flare classification had almost entirely concealed, which brings us back to the number that lied, an M1.9. Everything you have just seen, the hours-long burn, the shock wave ringing through the corona at somewhere between 800 and 1700 kilometers per second, the radiation storm crossing alert thresholds, a halo bright enough to earn a same-day storm watch, all of it came from a flare whose headline number suggests a middling, forgettable event. If the classification system can be that wrong about what an eruption means for Earth, what exactly is the classification measuring? And why does the entire warning architecture of modern space weather still lead with it? That question has a specific mechanical answer, and buried inside it is a precedent from April of 2023 that should change how you read every solar storm forecast you ever see again, including this weekend's. Part 4. Why Flare Class Lies. The letter and number system that graded Thursday's flare and M1.9 measures exactly one thing, and it is not the thing most people assume. Here is the system. Since the 1970s, satellites in the GOES series have stared at the Sun with X-ray sensors, measuring the total soft X-ray brightness of the entire solar disk, updated continuously. When a flare erupts, that brightness spikes, and the flare is graded by the height of the spike. An A-class flare is the faintest, then B, then C, then M, then X, and each letter step is a factor of 10. Within each letter, the number is a linear multiplier. An M2 is twice an M1, an X1 is 10 times an M1. The scale is tidy, objective, instantaneous, and machine-readable, which is precisely why it became the universal shorthand for solar violence. The letters themselves are bureaucratic fossils, M for medium, X for extreme, chosen decades ago with no expectation that they would one day headline news articles, and the X category was left open-ended at the top because nobody wanted to bet on how big the Sun could go. The largest flares ever measured have pushed the X numbering into the double digits and beyond, saturating the very detectors built to grade them. But notice what it grades. Peak brightness. The single highest instantaneous X-ray reading during the event. Not the size of the eruption, not the mass thrown into space, not the energy summed across the flare's whole lifetime. The classification answers one narrow question: how bright did the spike get at its brightest moment, and stays silent on the question that decides whether a cloud is coming for Earth, which is how much total energy the eruption moved and for how long. Think of it this way. Grade explosions by peak brightness and a camera flash outscores a house fire. The flash is blinding for a millisecond. The fire is dim by comparison at any given instant, but it burns for hours, and it is the one that takes down the house. Thursday's flare was a house fire. The peak said M1.9. Unremarkable. But the burn stretched across hours, and the energy that matters for lifting a coronal mass ejection is the integral, the total area under that long low curve. A patient M-class flare can move more total energy than an impulsive X-class flare that spikes spectacularly and dies in 4 minutes. The eruption that fired a billion-ton halo at this planet on Thursday is exactly that case. A modest peak stretched over so many hours that its cumulative output dwarfed its headline. Solar physicists have known this distinction forever, and it has a name you already heard: the long-duration event. Duration, not peak, is the property that correlates with coronal mass ejections. Impulsive flares frequently produce no CME at all flash and no ejector. Long-duration events are the CME factories because a reconnection process that persists for hours is a process that keeps pumping energy into lifting material long after the initial blast. When a forecaster sees a modest flare that refuses to end, attached to an erupting filament, they do not relax because the letter is M instead of X. They lean forward and wait for the chronograph frames because they know the number lies, and they know what the lie conceals. The system's blind spot is not an oversight, it is an inheritance. The X-ray classification was standardized in the 1970s because a satellite staring at the whole Sun could produce it automatically, instantly, and without human judgment, and in the 1970s that was the frontier of what operational monitoring could do. The things that actually predict a coronal mass ejection's punch, the duration of the burn, the mass in the cloud, the orientation of the magnetic field wrapped inside it, were either unmeasurable then or unmeasurable still. So the shorthand survived, and 5 decades later it shapes headlines, alert colours, and public perception, even though the profession itself reads a much longer list. When forecasters assess an eruption, the letter grade is one line among many. They look at how long the X-ray curve stayed elevated. They look for an erupting filament. They look for the Type 2 radio signature that certifies a real shock. They look at how bright and how wide the halo spreads. On Thursday's event, the letter grade was the only modest line on the entire sheet. Every other indicator, duration, filament, shock, halo, pointed the same direction and said the same thing: large. There is also a physical reason slow burns launch heavy clouds, and it comes down to what the energy is spent on. An impulsive flare converts its magnetic energy overwhelmingly into radiation and into accelerating particles, a detonation that lights up the spectrum and is over before anything massive can get moving. A long-duration event is the signature of reconnection that keeps running, field lines snapping and relinking beneath the rising structure hour after hour, and each round of reconnection does mechanical work, cutting tethers, pumping energy into the cloud's expansion, feeding the lift. The X-rays are almost a byproduct. The real budget is being spent hoisting a billion-ton structure out of a gravity well, patiently, the way a crane lifts what no explosion could throw. And if you want proof of how consequential that lie can get, you do not have to go back far. April 21st, 2023. The Sun produced a long-duration flare officially classified M1.7, a near twin of Thursday's by peak, and lifted a halo coronal mass ejection toward Earth. Forecasters saw it, modelled it, and issued a watch for moderate storming, reasonable, given the modest class and expected geometry. What arrived 2 days later ran over the forecast completely. The cloud's internal magnetic field turned out to be aimed strongly southward, the orientation that couples most efficiently into Earth's field, and the storm surged to G4 on the 5-step scale. Severe, 2 full levels above the watch. Aurora that night was photographed across an enormous swath of the United States, well down into states that see it perhaps once a decade. Nothing about the flare's classification hinted at that outcome, because the classification was never measuring the things that produced it: the duration, the mass, and above all the hidden orientation of the cloud's magnetic field. People who were outside that night in April of 2023 described the same disorienting experience from places that almost never see it. Sky watchers well down into the middle and southern tier of the United States, latitudes where the aurora is a once-in-many-years event, photographed red and green curtains climbing above their northern horizons, while the official scale scrambled upward behind the event. The storm had not been hyped in advance. There were no viral warnings, no breathless headlines in the days before, because the forecast, built honestly from the data available, had called for something moderate. The sky simply outran the paperwork. For the people watching, it was a free gift. For the forecasting profession, it was a documented reminder that the era of confidently bounding a storm's ceiling before measuring its magnetic field has not arrived, and every M-class halo since then has carried a quiet asterisk because of it. Hold that April 2023 storm in your mind as this weekend approaches, because the parallel is uncomfortably clean. Same flare class, within a rounding error, same long-duration signature, same halo geometry, same moderate-sounding watch. The 2023 case does not mean Sunday's storm will overperform. Glancing below geometry, which we will dissect properly later, argues for restraint, and most forecasts verify close to their central estimate. What the precedent establishes is narrower and more important. The error bars on this class of event are asymmetric. A long-duration M flare with a halo has a documented history of beating its forecast by multiple levels, and the mechanism of the beat, a southward magnetic field measurable only in the final hour, is sitting inside Sunday's cloud right now, unmeasured, exactly as it sat inside the 2023 cloud. This is the correct mental model for reading any storm watch, and it is worth stating plainly because you will use it for the rest of your life as a sky watcher. A geomagnetic storm forecast is not a single number, it is a distribution, and for events like this one, the distribution is lopsided. The downside surprises are shallow, a graze that misses cleaner than expected, a field that arrives pointing north, a quiet Sunday, and some disappointed photographers. The upside surprises are deep because the same hidden variable that can mute a storm can multiply it. When the watch says G1 to G2, the fine print, written in the physics rather than the bulletin, says most likely moderate, small chance of nearly nothing, and a thin, real tail in which the field arrives southward, and Sunday morning joins the list of nights people remember. Forecasters cannot narrow that tail before the cloud is measured. Nobody on Earth can. So here is where the story stands. A deceptively graded eruption has launched a genuinely large cloud at this planet. The shock front is confirmed and fast. The arrival window is Sunday morning, and the one number that will decide everything is hidden until the last hour. That is the main event, and everything so far has been about the projectile. But the projectile did not come alone. Hours after the flare peaked on Thursday, a different kind of storm reached Earth, one that travels not in days but in tens of minutes, one that has already crossed an official alert threshold twice while you have been watching this video's opening act. The cloud is still 2 days out, its advance guard is already here, and the story of what those particles are and what their strange flickering behaviour reveals about the shock racing ahead of the cloud is where we go next. Part 5. The First Warning Shot. 105 minutes. That is how long it took after the flare peaked on Thursday afternoon for the first physical piece of this event to reach Earth. Not the light. The light arrived in 8 minutes and 20 seconds, as it always does. Not the cloud either. The cloud is the slow freight, the billion-ton structure still out there in the dark right now, grinding through the solar wind toward its Sunday appointment. What arrived at 1845 Universal Time on July 30th was something in between. Protons. Hydrogen nuclei accelerated to enormous energies by the eruption, spiraling along the sun's magnetic field lines out into the solar system, moving at large fractions of the speed of light. They are the middle children of a solar eruption, slower than light, vastly faster than the ejecta, and when they arrive in force, forecasters call the result a solar radiation storm. Detectors on the GOS satellites count these particles continuously, and the count has a formal unit, the particle flux unit, a measure of how many energetic protons are streaming through each square centimetre of space every second from every direction of the sky. The energy benchmark that matters for the official scale is 10 mega-electronvolts, which deserves a moment of translation. A proton carrying 10 mega-electronvolts is moving at roughly 1/7 of the speed of light, fast enough to cross the Sun-Earth distance in under an hour if it flew straight, fast enough to punch through a sheet of aluminum foil and keep going, fast enough that no reasonable amount of spacecraft skin fully stops its most energetic cousins. On a quiet day, the flux of such protons idles at a fraction of 1 unit, a thin drizzle of galactic cosmic rays and solar stragglers. Space is never truly empty, but it is calm. Thursday evening it stopped being calm. The flux climbed through the evening, and at 2055 Universal Time it crested at 18.14 particle flux units, nearly double the threshold of 10 that defines the lowest rung on the official radiation storm scale. That scale is worth 30 seconds of your time because it is the S scale, the least famous member of the space weather alphabet, and it works logarithmically. S1, minor, begins at 10 particle flux units. Each step above it costs a factor of 10. S2, moderate at 100, S3, strong at 1000, S4, severe at 10,000, and S5, extreme at 100,000 particle flux units. The scale spans 4 factors of 10 between its floor and its ceiling, which means the difference between a minor radiation storm and an extreme one is a factor of 10,000 in particle flux. Thursday's event, peaking at 18, was a genuinely small S1, a storm that cleared the lowest bar on the ladder by less than a factor of 2, then held above threshold through the night before sliding back under at 7:15 Universal Time on Friday morning. So why does a small S1 deserve a full act of this video? 2 reasons, and the first is what it does. Even a minor radiation storm has a real physical footprint on human systems. Earth's magnetic field deflects incoming charged particles toward the poles, which means the radiation from an event like this funnels into the high latitudes. Aircraft on polar routes, the great circle shortcuts between North America and Asia that skim the top of the world, fly through the funnel. During radiation storms, the extra particle flux degrades high-frequency radio propagation across the polar caps, the very radio band those flights rely on where satellite coverage thins, and airlines respond to stronger events by shifting routes southward, trading fuel and time for communication reliability. Flight crews and frequent polar passengers absorb a slightly elevated radiation dose during such events, small at S1, worth monitoring at higher levels. And above the atmosphere entirely, radiation storms are one of the quantities astronaut flight surgeons track for spacewalk planning, because a spacesuit is a much thinner shield than a planet's worth of air. None of this made Thursday's event dangerous. All of it makes the category of event worth respecting, because the ladder those effects climb has 13 more factors, of 10 above where Thursday peaked, and history has used several of them. Climb that ladder briefly. because the upper rungs put Thursday's 18 units in their true context. At the strong and severe levels, thousands to tens of thousands of particle flux units, radiation storms stop being a footnote for airline dispatchers and become events spacecraft operators plan their week around. Energetic protons punching into a satellite do damage in two distinct ways. The slow way is accumulation, each particle depositing a whisper of energy in solar cells and electronics, aging the hardware, which is why satellite power systems are budgeted to lose capacity across their lifetimes. The fast way is the single event upset, one sufficiently energetic proton striking one sufficiently unlucky transistor flips a bit, corrupts a command, or triggers a phantom instruction, and suddenly $1 billion spacecraft is executing code nobody sent. During the greatest radiation storms of the space age, operators have watched star trackers blinded by particle static, cameras snowed with hits, and entire fleets placed in protective safe modes to ride the flux out. And for the human beings above the atmosphere, the calculus is starker still. The canonical cautionary tale dates to August of 1972, when a ferocious proton event erupted in the quiet months between two Apollo missions. Astronauts on the lunar surface or in transit, protected by little more than a spacecraft hull and fabric, would have absorbed a dose with real medical consequences. The gap in the schedule was luck, nothing more, and every space agency planning missions beyond Earth's magnetic shelter has been quietly running that arithmetic ever since. Thursday's S1 was 10,000 times too weak to threaten anyone. The mechanism that made it is the same mechanism that made 1972, running at a lower setting attached to the front of the cloud arriving this weekend. The second reason matters more for our story. It is what the protons reveal. Energetic protons from a solar event reach Earth by two different mechanisms, and telling them apart is a genuine diagnostic art. Some are accelerated in the flare itself, flung outward in the initial reconnection blast, an impulsive population that rises fast and fades fast, the particle equivalent of the camera flash. Others are accelerated continuously by the shock front driven ahead of the coronal mass ejection, the same shock the Type II radio burst certified, which surfs through the solar wind energizing particles the whole way out, like a wave pushing surfers ahead of it. That population rises more gradually, lasts longer, and critically, it can keep arriving and keep intensifying for as long as the shock stays healthy and magnetically connected to Earth. The aviation response to these events is more procedural than most passengers ever learn. Airline dispatch offices subscribe to space weather alerts the same way they subscribe to volcanic ash advisories, and a radiation storm triggers a defined decision tree. Check which scheduled routes cross the high latitude thresholds, weigh the communication degradation against the cost of a southern deviation, and, for stronger events, factor in the dose. Aircrew are formally classified in several countries as radiation workers, their cumulative annual exposure tracked, because a career at high altitude and high latitude accumulates a measurably larger dose than a career at sea level. An S1 adds a rounding error to that ledger. The scale's upper rungs are the reason the ledger exists. Thursday's event had the fingerprints of the second kind. The onset came nearly 2 hours after the flare peak. The profile was gradual, and the event stretched across more than 12 hours, from mid-evening Thursday to early Friday morning. There was even a brief excursion in a far more energetic channel. For a short window, protons above 100 mega-electron volts, particles carrying 10 times the benchmark energy, pushed above 1 particle flux unit. That 100 mega-electron volt population is the one that matters for the deepest effects. The particles energetic enough to punch through spacecraft shielding and, in extreme events, to shower secondary particles down through the atmosphere itself. Its brief appearance here, at low intensity, was another size marker. Small storm, but a real engine behind it. Put the pieces in one sentence, and keep your eye on the thread that runs through this whole video. The modest flare that would not stop erupting drove a shock strong enough to ring the corona in radio and to accelerate a radiation storm to Earth within 2 hours, and that shock is attached to the front of the same cloud, arriving Sunday morning. The protons are not a separate story. They are the cloud's calling card delivered 2 days early. And by dawn on Friday, the calling card seemed complete. The flux slid back below threshold at 7:15 Universal Time. The event was declared over. Space began settling back toward its eerie background calm. It stayed settled for a little over 6 hours. Part 6. Flickering at the threshold. At 1336 Universal Time on July 31st, the proton count at Earth crossed 10 particle flux units for the second time in 2 days. 1 minute later, at 1337, the Space Weather Prediction Center issued a fresh alert. Solar radiation storm, S1, minor, once again in progress. Then, 24 minutes after that, the storm appeared to vanish. The 1400 Universal Time reading came in at 8.90 particle flux units, back below the threshold. By 1406, the agency's live display showed S0, no storm. Yet the S1 warning itself remained in force, valid through 1 minute to midnight, Universal Time on July 31st. If that sequence sounds contradictory, Storm declared, storm gone, warning still active, you have just discovered the difference between physics and bookkeeping, and the gap between them is one of the most quietly revealing corners of this entire event. The bookkeeping side is simple. The S-scale is threshold-based. Flux above 10 units, storm. Flux below 10 units, no storm. The rule is clean and objective, which is what you want from an operational alert system that has to trigger automatically at 3 a.m. without a committee. But nature does not respect clean rules. The actual quantity, the proton flux, is a continuous wandering curve, and on Friday that curve was drifting along almost exactly at the threshold line, brushing over it, sagging under it, hovering. 18.14 on Thursday was a clear crossing. 8.9 at 1400 Friday was a near miss. 10-point-something at 1336 was technically a storm. The difference between an official radiation storm and officially quiet space on this particular Friday was a flux variation smaller than the wobble the detectors see over an ordinary afternoon. So forecasters did the sensible thing the bureaucracy allows. They kept the warning standing. The warning through 2359 is a professional judgment translated into paperwork, and the judgment reads, "This curve is going to keep flirting with the line all day, and we would rather hold the alert than reissue it every 90 minutes as the flux breathes. It is the space weather equivalent of leaving the flood warning up while the river oscillates around bankful, and it tells you the forecasters expect the source of these particles to keep producing." Which brings us to the physics side, the interesting side. Where are these second-wave protons coming from? The flare is long over. The impulsive population from Thursday's blast dispersed. A fresh crossing on Friday afternoon, half a day after the first event decayed, is very hard to explain with anything anchored at the sun, and very easy to explain with something that is no longer at the sun. A shock, out in interplanetary space, still driving, still accelerating particles as it goes, its efficiency waxing and waning as it eats through different stretches of solar wind, its magnetic connection to Earth strengthening and slipping as geometry evolves. The cloud and its shock are somewhere in the middle third of the Sun-Earth gap as Friday unfolds, and a shock at that distance showering Earth with marginal, threshold-hugging proton flux is exactly the profile you would draw on a whiteboard if asked what a healthy inbound CME should look like from 2 days out. To appreciate why the connection between that distant shock and our detectors comes and goes, you need one piece of solar system architecture. The sun's magnetic field does not extend outward in straight lines. The sun rotates, once roughly every 27 days, and as it rotates, it winds the field lines it releases into an enormous spiral, the same shape a rotating garden sprinkler prints on a lawn. Charged particles cannot travel freely across magnetic field lines. They spiral along them, beads on a curved wire. So whether Earth receives particles from a shock depends not on whether the shock is pointed at us, but on whether the particular spiral field line threading through Earth at that moment also threads back through the shock's surface. As the sun turns and the shock expands, that geometry continuously rewires itself. Connections form, strengthen, slip and reform, and the proton flux at Earth breathes accordingly. Friday's threshold-hugging flicker is exactly that breathing, rendered in data, a fluctuating hotline to a shock front no telescope can image, its signal strength rising and falling with the geometry of an invisible spiral. Read that way, the flickering stops being a bureaucratic curiosity and becomes a live telemetry channel from the thing this whole video is tracking. Thursday's protons said, a shock has formed, and it works. Friday's protons say, the shock is still out there, still working, still connected to us. Every threshold flirtation is a status ping from a structure no camera can currently see, because a coronal mass ejection in transit is, for most of its journey, invisible. The coronagraphs watched it leave. The next direct measurement comes only when it arrives at the monitoring spacecraft stationed upstream of Earth. In between lies a gap of more than a day in which the storm exists only as models, probabilities, and these faint radioactive knocks on the door. Forecasters read these proton profiles the way a doctor reads a pulse, and the craft has real diagnostic depth. A profile that spikes and decays smoothly says impulsive flare source, no lasting engine. A profile that grows, plateaus, and refuses to die says driven shock. A profile that surges suddenly after days of decline often marks the moment the shock itself sweeps past the detector. A phenomenon distinct enough to carry its own name in the literature, the energetic storm particle event, and it is one of the tells that can announce a CME's arrival minutes before the magnetic data confirms it. Friday's pattern, decay, silence, recrossing, hover is the middle chapter of that grammar. It is what a connected, functioning, inbound shock writes in the particle record from mid-crossing. The eruption's advance guard, in other words, is still reporting for duty, and its continued presence quietly raises confidence in the one claim everything this weekend depends on. The cloud is real, it is coherent, and it is still coming. The warning's midnight expiry sets up tonight's small suspense, the subplot running underneath the main countdown. If the flux sags away from the threshold through the evening, the warning lapses quietly at 1 minute to midnight, and the radiation chapter of this event closes with a whimper, exactly as the bookkeeping expects. If instead the flux firms up as the night wears on, holding near 10, brushing over it, the forecaster's decision renews itself. Extend again, and note in the log that the shock's output is not decaying the way a fading source should. Either outcome is informative. A proton curve that dies on schedule says the shock is weakening as it climbs the last stretch toward Earth, consistent with the drag story and a softer arrival. A curve that keeps flickering into Saturday says the engine out there retains more punch than the median forecast assumes. It is a strange kind of weather report reading tomorrow's storm in the static of today, but it is one more example of the theme this event keeps teaching. The cloud communicates, constantly, to anyone fluent in its channels. There is one more consequence of proton events worth pinning here, because it may become relevant this weekend. When energetic protons funnel into the polar atmosphere, they ionize the lower layers of the ionosphere over the caps, and that ionization absorbs high-frequency radio waves rather than reflecting them. The phenomenon is called polar cap absorption, and during strong events it can black out shortwave communication across the entire polar region for days. At swan strength, the effect is marginal, degradation, not blackout. But if the flux climbs again as the shock closes in, and shock arrival is historically a moment when proton events surge, the polar radio picture on Sunday morning could sour at exactly the hour the geomagnetic storm begins. Two different storms from the same eruption, radiation and geomagnetic, arriving stacked. Remember the possibility. The forecast does not require it, but this event has already shown a taste for refusing to end on schedule. Step back and look at what the last two parts have established, because the picture has quietly inverted. The dramatic thing, the visible thing, the halo in the coronagraph is days away and silent. The invisible thing, the particle wash, is here now, flickering at the edge of official existence, and between them stretches the question the next part takes head on. What exactly is happening out there in the gap, in the 93 million miles of dark between the camera's last frame and the moment the cloud makes landfall on our magnetic field? The answer involves a crossing that physics makes surprisingly hard to time, and a strange, almost suspicious stillness at the destination. Part 7. 93 million miles to go. Picture the space between the Sun and the Earth as an ocean, because right now that ocean has a ship on it. The distance is 93 million miles, 150 million kilometers, the span astronomers call 1 astronomical unit. Light crosses it in 8 minutes. The fastest spacecraft humanity has ever flown take weeks. Sunday's cloud is making the crossing in about 2 days, which, for an object the size of dozens of Earths carrying roughly 1 billion tons of star matter, is a remarkable pace, and yet the crossing is anything but a straight cruise at constant speed. It is a continuous fight between momentum and drag, and how that fight goes decides when the storm starts. We saw the drag mechanism when we unpacked the shock speeds. A fast cloud ploughs up the wind ahead of it, sweeps mass into its sheath, and pays for every ton with speed. What that means for the timeline is that a coronal mass ejection's launch speed is a poor guide to its arrival speed. A cloud that leaves the corona at 1700 km per second, the upper of our two shock estimates, does not hold 1700. It sheds speed hour after hour, asymptotically approaching the pace of the wind around it. The modeller's craft lies in guessing the decay curve, and the decay curve depends on the thing no one can fully measure in advance, the state of the ocean along the specific corridor the cloud will sail. That ocean, this week, is peculiar. The solar wind flowing past Earth as the countdown runs is moving at 302 km per second. To calibrate you, the slow wind ranges around 3 to 400, the fast streams from coronal holes run 5 to 800, and the ambient average sits in the low 400s. 302 is scraping the bottom of the sun's registered output, a becalmed sea. For the crossing, a slow ambient wind is a double-edged inheritance. It means more velocity difference between cloud and medium, hence more drag per ton swept, an argument for a later, softer arrival. But it also means the corridor's density and structure carry the memory of the week's earlier traffic, and this corridor had traffic. The flurry of coronal mass ejections late last week that had forecasters posting storm watches for the 29th through the 31st. If those earlier ejecta swept the lane partially clear, the drag tax drops, and the cloud arrives earlier and harder than a becalmed ocean model expects. Two competing corrections, opposite signs, neither measurable from here. That is the honest texture of arrival forecasting. Now do what the models did and put numbers on the window. Even the starting line is soft, and that is unusual. For an impulsive eruption, launch time is a clean timestamp, but Thursday's event released its cloud across a burn that lasted hours, so the honest launch entry reads, Thursday, 1700 Universal Time, give or take the hours the long eruption smeared across, with the coronagraph's first clear frames as the anchor. Distance, 1 astronomical unit. Hold 850 km per second the whole way, the slower shock estimate, and the crossing takes about 49 hours, landing you around 6 p.m. Universal Time Saturday. Hold 1700, the faster estimate, and you arrive in roughly 24 hours, Friday evening, which plainly is not happening. The quiet upstream data already rules it out. For calibration, the record books show what the crossing looks like when the sun is not merely strong but relentless. The Great Storm of 1859 crossed in well under a day. The famous August 1972 event set the modern record at around 14.5 hours, and the 2012 superstorm we dissected in our video from July 23rd made the trip in about 19 hours, and in every one of those cases researchers found the same enabling trick. Earlier eruptions had swept the lane clear, so the monster behind them ran on an open highway. Sunday's cloud is no monster, and its lane is only partially swept, but the principle scales all the way down. Transit time is not a property of the cloud alone, it is a property of the cloud and the road. Fold in drag, the halo fitting, and the ensemble of model runs, and the official answer emerges, arrival early Sunday, August 2nd, with the geomagnetic response peaking at a forecast KP of 5.67 in the window from 6 to 9 Universal Time. We will unpack KP properly soon. For now, read it as the planetary Richter scale for magnetic disturbance, and 5.67 as the forecast saying, moderate storm most likely, with the peak in that 3-hour morning window. Translate the window out of Universal Time and the practical shape of the weekend appears. 6 to 9 Universal Time on Sunday is 2 to 5 in the morning on the American East Coast, 1 to 4 in the Central Zone, midnight to 3 Mountain, and 11 p.m. Saturday to 2 a.m. Sunday on the Pacific Coast. In other words, for North America, this is a Saturday night storm. The forecast peak lands squarely in the post-midnight hours when aurora viewing is at its darkest and best, a coincidence of celestial mechanics and time zones that aurora chasers from Washington state to Wisconsin to upstate New York should notice now and plan around. If the storm runs on schedule and reaches its G2 potential, the northern tier of the United States gets its show during prime viewing darkness, not lost in daylight the way so many good storms are for any given longitude. Half of every geomagnetic storm's audience is always on the wrong side of the planet when the peak hits. This time, if the schedule holds, North America is on the right side. One refinement matters for anyone planning to actually watch. Arrival and peak are not the same moment, because a coronal mass ejection is not a wall, it is a sequence. The first thing to reach Earth is the shock, a sharp discontinuity where the solar wind speed, density and field strength all jump in seconds. When that front slams into the magnetosphere, ground observatories register an abrupt compression, a jolt in the field recorded simultaneously across the planet, the traditional opening bell of a storm. Behind the shock comes the sheath, hours of hot, turbulent, compressed wind, the ploughed snow shaking the field chaotically. Only after the sheath passes does the main body arrive, the ejector itself, the magnetized core of the cloud, and it is typically there, deep in the structure, that the strongest and most sustained storming develops if the internal field cooperates. The whole procession can take many hours to march past a planet. So when the forecast places first arrival early Sunday and the KP peak at 6 to 9 Universal Time, it is describing that anatomy: contact, then build-up, then crescendo. Sky watchers who step outside at the first alert see nothing, and go to bed have misread the structure of the event. The opening bell is not the show, but hold that phrase. If the schedule holds, at arm's length, because arrival forecasts of this kind carry error bars of 6 to 12 hours as a matter of routine, and this particular event wears its uncertainty openly. A factor of 2 disagreement in its measured launch speed, a corridor of unknown drag, an eruption so prolonged that even the starting gun is smeared. The storm could walk in at midnight Universal Time and catch Europe's Saturday evening instead. It could drag its feet into Sunday afternoon and hand the show to Asia. The 3-hour window in the forecast is a centre of probability, not a promise, and every experienced sky watcher treats it accordingly. You start checking the data Saturday evening, and you keep checking until the numbers move. Which raises the operative question. Checking what, exactly? What does it look like when a billion-ton cloud makes landfall on a planet's magnetic field, in the data, in real time? To answer that, you first have to see just how flat the instruments are reading right now, because the stage on which this storm will land is, at this moment, one of the quietest Earth's space environment has offered all summer, and that quiet is about to become the most useful measuring stick this event has. Part 8. The Quiet Before. There is a number sitting in the observatory feeds right now that should not belong in the same week as everything you've heard so far. That number is 1.67. It is the highest the planetary K-index, the KP, has managed in the current observing window. And to understand how strange that is, you need to know what KP actually measures, because this index is about to become the main character of Sunday morning. The number every alert, every app notification, and every aurora forecast will be built on. Here is the machinery behind it. Scattered across the globe, from Scandinavia to Australia, a network of magnetic observatories runs instruments that do nothing but record the strength and direction of Earth's magnetic field continuously to extraordinary precision. When space is calm, their traces draw smooth, gentle daily curves, the field breathing with the tides of the upper atmosphere. When a storm couples into the magnetosphere, those traces go ragged, jumping and swinging as vast electrical currents surge through near-Earth space and induce disturbances on the ground below. Every 3 hours, each observatory grades the raggedness of its own trace on a scale from 0 to 9. The readings are combined and weighted across the network, and the result is the planetary index, a single number summarizing how hard the entire planet's magnetic field is being shaken. 0 and 1 are deep calm. 3 is unsettled. 5 is the threshold of an official geomagnetic storm, the G1 level. 9 is reserved for the historic extremes, the storms that get names and anniversaries. And the scale is quasi-logarithmic, each step upward representing far more than an equal increment of disturbance. KP 1.67 means the needles are barely moving. It means the great current systems that ring the planet during storms are idling. It means the aurora, which never fully disappears, has shrunk back to a thin, dim crown around the poles, its total power output in the low tens of gigawatts, the quiet sky floor. Add the rest of the upstream readings, solar wind limping past at 302 kilometers per second, the interplanetary magnetic field's north-south component sitting at a negligible -2 nanotesla, and you have a portrait of near-total geomagnetic stillness. On the scale of the space around this planet, it is one of the flattest stretches of the summer. Even that -2 deserves a sentence, because you now know what the letter B and the letter Z mean when they travel together. The field draped past Earth at this moment does lean faintly southward, the geo-effective direction, the orientation that opens the door. But magnitude is everything. 2 nanotesla of southward field is a whisper against the door, a coupling so weak it cannot spin up the current systems in any meaningful way, which is precisely why the KP sits below 2. During major storms, the southward component measured upstream can reach 10, 20, in the historic cases 50 nanotesla and beyond, and it can hold those values for hours. The quantity forecasters will be staring at on Sunday morning is this exact number, this BZ, and the entire drama of the arrival will be watching it either dive or fail to dive. Today it idles at -2, a reminder that the dial exists resting near 0, waiting for the hand that is currently 2 days away to grab it. And that flatness, hold the thread, is the stage onto which a billion-ton cloud is scheduled to walk sometime in the next 36 hours. The contrast deserves savouring, but it also deserves suspicion, because your intuition wants to read the quiet as a contradiction. How can a storm be coming if everything is this calm? The answer is that the calm and the storm are not in tension, they are in sequence, and the reason is nothing more mysterious than distance and speed. The eruption's light reached us in minutes, its protons arrived in under 2 hours, but the disturbance that moves needles on the ground rides with the mass, and the mass is still in transit. Geomagnetic conditions at Earth are a strictly local measurement. They tell you what is here, and nothing about what is en route. A magnetometer cannot feel a cloud that has not arrived, any more than a beach feels a tsunami still 500 miles offshore. Flat water at the shore is not evidence against the wave. It is simply the last hours of the old regime. In fact, for the people whose job is to catch the arrival, the quiet is a gift, and it is worth understanding why. Storm detection is a signal-to-noise problem. When the background is already churning, when Earth is inside a fast stream from a coronal hole, or still ringing from an earlier impact, the arrival of a new shock can be genuinely ambiguous. A step change buried in noise, and forecasters can argue for hours about whether and when a CME actually arrived. That matters, because the arrival time is the anchor for everything downstream, the storm's expected duration, the timing of its peak, the verification of the model that predicted it. This weekend offers the opposite regime. Against a baseline of KP1, a wind of 300 and a field as flat as this one, the shock's arrival will be unmistakable, a vertical cliff in every upstream trace, a simultaneous jolt in every ground observatory, a timestamp nobody will dispute. Whatever Sunday brings, the record of it will be clean. This event, whatever its final size, will be one of the best documented moderate storm arrivals of the cycle, a natural experiment prepared under laboratory conditions. The quiet also sharpens the human side of the story, the part happening in office chairs rather than in space. Consider what the last week has looked like from a forecast desk. Late last week, the sun sent earlier eruptions this way, and watches went up for the 29th through the 31st at levels reaching G3. The anticipation, the alerts, the model runs, and then quiet. KP 1.67 quiet, as arrivals under-delivered at Earth even as new eruptions kept leaving the sun. Now a fresh halo, a fresh watch, a fresh countdown into a weekend. Forecasting the sun in a week like this is a discipline of professional patience. The star keeps loading the gun, the models keep projecting arcs, and the ground truth keeps its own schedule, indifferent to bulletins. If Sunday verifies, the weekends as a textbook save for the new observing chain. If Sunday fizzles, the same chain gets a lesson in humility, and either way the desks will be staffed and watching through the small hours of the morning. Between now and the arrival, the forecast itself will not sit still either, and knowing its rhythm turns you from a spectator into a reader. The 3-day outlook gets reissued daily, folding in the newest model runs. If analysts revise the CME's fitted speed or direction from additional imagery, the arrival window shifts, and a shift of even 6 hours redraws which continents get the show in darkness. The synoptic discussions, the prose products written by human forecasters for pilots, grid operators, and enthusiasts who read past the headline number, will sharpen their language as confidence firms. By Saturday evening, the entire state of knowledge about this cloud will have compressed into its final pre-arrival form, a window, a probability, and a list of things that cannot be known until the buoy upstream rings. Watching that progression happen in the public product's forecast, revision, refinement, arrival is watching the scientific method run at weekend speed, in the open, on a deadline set by a star. There is one more reading of the stillness worth naming, the one this channel keeps returning to because it reframes everything. The quiet is not the absence of the story. It is the measurement of what the story will be judged against. Every gigawatt the auroral ovals gain this weekend, every step the KP ladder climbs, every degree of latitude the light pushes south will be measured from this floor, this 1.67, this becalmed Friday. The sun has already done its part. The eruption is over and the cloud is committed. Earth has already done its part, the baseline is set, and the instruments are zeroed. Everything now rests on the collision, and the collision has a geometry problem that we have been postponing since the first minutes of this video, because the forecast does not say the cloud will hit us, it says the cloud will graze us, and the difference between those two words contains nearly all of the remaining uncertainty about Sunday morning. Part 9. The graze. Every forecast you have heard in this video, the G1 to G2 range, the KP 5.67, the aurora reaching for New York, rests on a single geometric judgment made from a handful of camera frames, the judgment that this cloud's heart is not aimed at Earth. Its shoulder is. That is what a glancing blow means, and the stakes hiding inside that phrase are larger than they sound. A coronal mass ejection is not a cannonball with a single trajectory. By the time it reaches Earth's distance, it is a continent of plasma tens of millions of kilometers wide, and different parts of it deliver profoundly different experiences. Take the anatomy you already know, shock, sheath, core, and now add the crucial refinement. That anatomy is layered around an axis. Down the middle of the cloud runs its heart, a structure physicists call a flux rope, a tightly wound helix of magnetic field lines coiled like the strands of a cable, carrying the strongest and most smoothly organized fields in the entire structure. And you have already met this rope in its previous life. The filament from Part 1, the dark snaking channel of cool plasma that hung suspended over active region 4492 for days before the eruption cut it loose, was the visible tracer of this very helix. The magnetic hammock that levitated the filament was the rope, photographed in silhouette. When the eruption tore it free, the rope did not dissolve. It expanded, carrying its coiled architecture with it, swelling from a structure the length of several Earth-Moon distances into a continent of organized magnetism tens of millions of kilometers across. The dark snake you could have watched on the solar disk on Wednesday is, in a physically continuous sense, the object whose orientation will decide what Sunday morning looks like. Few chains of cause and effect in nature are this traceable. A shadow on a star on Thursday, a number on a dial at Earth on Sunday. Pass through the center of a CME and you traverse the full sequence at full strength. Hard shock, thick violent sheath, and then hours inside the rope itself, where the field is intense, steady, and capable of sustained deep coupling with Earth's field. Pass through the flank and everything thins. The shock is oblique and weaker. The sheath is shallower, and the flux rope, the storm's engine room, may brush past to one side entirely, leaving you with the cloud's turbulent outskirts rather than its organized heart. The model's verdict from fitting Thursday night's halo frames is that Earth gets the flank. The cloud's central axis points some degrees off the Sun-Earth line, and what sweeps over this planet on Sunday should be the shoulder. A real shock, a modest sheath, a side swipe from the ejector's edge. Feed that geometry into the coupling equations and out comes the watchers issued. G1 likely, G2 possible, KP peaking in the 5s, everything consistent, everything reasonable. Now for the part the bulletin cannot fully convey. Glancing blows are the least reliable forecasts in space weather, and the unreliability is structural, not a matter of effort. 3 separate uncertainties stack, and they all push on the same lever. First, the direction estimate itself is soft. A halo CME is the hardest kind to measure precisely because it moves mostly along the line of sight, where a coronagraph's 2-dimensional view compresses all the depth information. Analysts reconstruct the cone of the eruption from how the halo brightens asymmetrically, and the answer carries error bars of many degrees. For a central hit, 10 degrees of error changes little. For a graze, 10 degrees is the whole game. Tilt the cone slightly earthward, and the flank becomes a shoulder and chest impact. Sheath and rope both engaged. Storm levels a category or more above the watch. Tilt it slightly away, and Earth catches only the shock's dying edge, a brief flutter of unsettled conditions, and the aurora forecast evaporates. The difference between those futures is smaller than the measurement's honest uncertainty. That is not a criticism of the analysts. It is the plain arithmetic of measuring depth with a flat image. The rare occasions when nature has allowed a direct check on these reconstructions only deepen the humility. A handful of times in the space age, a coronal mass ejection has happened to sweep over two spacecraft at once, one near Earth and one elsewhere in the heliosphere, sampling the same cloud at 2 points hundreds of thousands or millions of kilometers apart. The comparisons are sobering. Field orientations that differ meaningfully between the two crossings, arrival times off from single-point predictions by hours, structures that one spacecraft records as a textbook flux rope and the other as a tangled mess. The lesson is not that the models are bad. The lesson is that a CME is a three-dimensional, evolving, internally structured object, and any forecast built from one viewing angle is an act of disciplined extrapolation. Forecasters know this better than their critics do, which is why the honest ones speak in ranges and probabilities even when the public wants a verdict. Second, clouds deform. The corridor between here and the sun is not uniform, and a CME ploughing through structured wind does not keep its launch shape. Simulations and multi-spacecraft encounters have shown ejector pancaking as they expand, flanks curling, axes rotating tens of degrees mid-flight. The object the halo frames measured on Thursday night is not identical to the object arriving Sunday. It has spent 2 days being kneaded by the heliosphere, and the kneading can move the engine room. And third, towering over everything, is the orientation problem, the one this video has been circling since part 4, because now is when it fully lands. Even a flank encounter delivers magnetized plasma to Earth's doorstep, and the storm that results depends overwhelmingly on a single property of that plasma, the direction its magnetic field points, moment to moment as it streams past. The physics is called magnetic reconnection, and the rule is brutally simple. Earth's magnetic field points northward on the day side, where it meets the wind. If the incoming cloud's field arrives pointing northward too, the two fields press against each other like matched magnets. The door stays shut and even a large, fast cloud slides around the magnetosphere, delivering little more than a compression and a shrug. If the incoming field points southward, opposite to Earth's, the field lines splice, the door swings open, and the cloud's energy pours down the connection into the magnetosphere, driving the currents, the heating, and the aurora that define a storm. North, a shrug. South, a storm. The stronger the southward field and the longer it holds, the deeper the storming runs. That north-south component has a name you will see on every serious space weather dashboard: BE. And here is the fact that should genuinely unsettle you, the fact that makes this entire multi-billion-dollar forecasting enterprise feel like a magic trick performed blindfolded. Bees cannot be measured in advance, not by any instrument humanity operates. The orientation of the field wound inside that flux rope, the single variable that decides whether Sunday is a whisper or a show, is invisible to every camera, every radio antenna, every model. It becomes known at exactly one moment, when the cloud physically sweeps over the monitoring spacecraft stationed 1 million miles upstream, minutes before it reaches Earth. Until then, 5.67 is a statistical guess about a coin already spinning in the dark. A word, too, about that strangely precise number in the forecast, the KP 5.67, because numbers like it are widely misread. No one believes the storm will peak at exactly 5.67 rather than 5.5 or 6.1. The decimals are an artifact of how the prediction is made. Models generate KP in thirds of a unit, ensembles of runs get averaged, and the arithmetic emits a number with more digits than the underlying physics can honestly support. Professionals read 5.67 as a range statement. High fives, most likely, the upper half of G1 brushing G2, and the false precision survives in public bulletins simply because machines wrote it. It is worth internalizing this habit of translation, because the gap between how precise a forecast sounds and how precise it is happens to be the exact space where both disappointment and conspiracy theories are born, a subject we will be visiting before this video ends. You have seen what happens when the coin lands wrong side up for the forecast. April of 2023, the M1.7 twin of this event, forecast moderate, arrived southward, ran to severe. That is the live tail risk inside Sunday's watch, and it coexists, honestly and simultaneously, with the live possibility that the Greys under-delivers and the whole weekend passes at KP4 with a faint glow on Minnesota's horizon. Both futures are in the cone. The bulletin's clean little range, G1 to G2, is the visible tip of a probability distribution whose edges span from nothing to memorable. So rather than pretend to a certainty the data cannot support, do what the professionals will do this weekend. Hold the range and prepare for its edges, which means the practical question is no longer when or whether. It is, what does each rung of the ladder actually deliver? If Sunday morning lands on target, what does a G2 morning look and feel like on the ground, in the sky, in the world's infrastructure? That question has a specific, satisfying answer, and it is the next stop. Part 10. If G2 arrives. Sunday morning, 6 Universal Time. Somewhere over the Atlantic's darkness the needles jump, the alerts fire, and the storm the world has watched cross 93 million miles finally has a measured strength. Suppose the forecast verifies. Suppose the peak reads KP6. What actually happens? The framework for the answer is the G-scale, NOAA's 5-step ladder for geomagnetic storms, and it maps directly onto the KP index you now understand. KP5 is G1, minor, KP6 is G2, moderate, KP7 is G3, strong, KP8 is G4, severe, KP9 is G5, extreme, the rung reserved for the historic events. The ladder's virtue is honesty through specificity. Each rung comes with a documented menu of expected effects, compiled from decades of storms, so that a 2-word classification carries an entire operational briefing inside it. Walk the G2 menu, and you walk through Sunday's most likely morning. Start with the sky, because the sky is where most of this channel's audience will meet the storm. The aurora exists permanently as an oval crown around each magnetic pole, fed by the standing trickle of solar wind coupling. What a storm does is pump the system. More current, more particles accelerated down the field lines, more atmosphere lit up, and the ovals both brighten and expand equatorward. At G2, the expansion typically brings the visible aurora down to around 55 degrees geomagnetic latitude. And here you need the crucial translation. Geomagnetic latitude is measured from the magnetic pole, which sits displaced from the geographic pole toward North America. That displacement is a standing gift to the United States. It means the same storm reaches farther south in America than in most of Europe or Asia. 55 degrees geomagnetic, drawn on a map of North America, is a line running through the northern tier of states, and it is exactly why the agency's own bulletin for this event names New York, Wisconsin, and Washington state as the potential southern edge of visibility, not as hype, as cartography. If you live along or above that line, here is your practical briefing, assembled from every storm this channel has covered. Get away from city light. Even 20 minutes helps enormously. Find an open northern horizon, a lakeshore, a ridge, a field. Let your eyes adapt for a genuine 15 minutes. No phone screen. Look north and low first. At the edge of visibility, the aurora often appears not as dancing curtains overhead, but as a pale, structured glow hugging the horizon, easily mistaken for distant city light until it moves. Use your camera. A modern phone on night mode, held steady for a 3-second exposure, sees colour and structure your eyes cannot, and many first-time aurora photographs are taken by people who saw almost nothing unaided. Check the real-time KP and aurora oval charts, rather than trusting a fixed schedule. Storms breathe and substorms, the sudden brightenings that make the whole night worthwhile come in surges an hour or two apart. And remember the anatomy from earlier. First contact is not the peak. The best of a storm frequently arrives hours into it, deep in the flux rope's passage. Now the infrastructure side of the menu, the part happening whether or not anyone is watching the sky. At G2, power grids at high latitudes may see what the scale calls voltage alarms and transformer heating on long transmission lines. The mechanism deserves one clean sentence, because it is the mechanism that scales all the way up the ladder. A geomagnetic storm makes Earth's field shake. A shaking magnetic field induces currents in any long conductor beneath it, and the continent-spanning power lines of the modern grid are, from the storm's point of view, antennas conveniently laid out to receive it. At G2, those induced currents are a nuisance, watched by control rooms, managed by procedure, logged and forgotten. Why the same physics at higher rungs becomes a civilizational concern is a story we told properly in our July 5th video on the power grid, and everything in it scales from the same humble alarms that may blink on this Sunday. Satellites feel a G2 morning too, in two distinct ways. The first is drag. Storm energy dumped into the upper atmosphere heats it, and heated atmosphere swells upward, thickening the wisp of gas at orbital altitudes. Every object in low orbit feels increased friction. Orbits decay a little faster, and operators rerun their tracking solutions. The dramatic sealing of that effect, an entire batch of freshly launched satellites dragged down by a minor storm in February of 2022, is a case we have covered before, and it began with exactly this mechanism at barely G1 strength. The second is charging, the slow electrical stress that storm-stirred particle belts impose on spacecraft electronics, the invisible hazard we dissected in our video from July 27th, and Sunday's storm, whatever its size, will stir that same belt and add its increment to the tally. High-frequency radio at high latitudes may fade in and out as the ionosphere churns. Precision GPS applications, surveying, agriculture, aviation approaches can degrade at the margins, and the mechanism is elegant in its indirectness. Satellite navigation works by timing signals through the ionosphere. The storm roughens the ionosphere, and the roughness translates into meters of position error for systems engineered around centimeters. Airline dispatchers watching the polar routes will fold the geomagnetic picture in with the proton picture from Part 6 and decide whether any flights shift south. Behind each of those bullet points stands a room of people whose Saturday night just changed shape, and the staffing tells you how seriously the quiet professional world takes a G2. The National Space Weather Desk runs around the clock regardless, but a watch weekend sharpens it. Model runs reissued as fresh data arrives. Coordination calls with grid reliability authorities who maintain formal geomagnetic disturbance procedures, notifications flowing to satellite operators who respond by postponing orbital maneuvers and delaying non-essential commanding until the environment settles, because you do not fire thrusters or upload software into a magnetosphere mid-tantrum if the burn can wait until Tuesday. None of these people expect Sunday to be historic. All of them will treat it as if it could be, because the marginal cost of readiness is an overtime shift, and the cost of the alternative on the wrong weekend is the subject of the next part. Since the sky's the headline, spend one more minute on what the light actually is, because knowing the mechanism deepens the seeing. The colours of the aurora are the emission lines of Earth's own air, struck like piano keys by particles raining down the field lines. The dominant green, the colour of virtually every aurora photograph, is oxygen, glowing from about 100 to 200 kilometres up. The rarer deep red that crowns great storms is oxygen again, but from higher altitudes, where the atmosphere is so thin that the atoms can complete a slow, delicate transition without being interrupted by collisions, a glow so fragile it only appears when the rain of particles reaches exceptionally high and hard. The purples and blues fringing the bottom edges of active curtains are nitrogen. When a display is strong enough that its red component stretches far above the horizon, observers hundreds of miles south of the main oval can see a crimson wash in their northern sky, which is why the great historical storms produced reports of red skies from latitudes that never otherwise see aurora at all. If Sunday morning's edge reaches New York and Wisconsin, it will most likely arrive as exactly that. Not overhead curtains, but a low green arc, perhaps with red reaching above it, strengthening and fading in surges as the magnetosphere pulses. Those surges have a name: substorms, spasms of the magnetotail snapping energy loose every hour or two, and they are the reason patience is the aurora watcher's cardinal virtue. The sky does not perform continuously. It performs in sets, and that is the whole G2 menu. An aurora show for the fortunate latitudes, a busy night shift for a few control rooms, a rounding error for everyone else. If Sunday delivers exactly the forecast, it will be a beautiful, minor, thoroughly well-measured event, the kind of storm a healthy civilization treats as a fire drill with a light show attached. But you have now seen, twice, why the forecast is a distribution and not a promise, and distributions have tails. The obvious next question, the one this channel exists to ask properly, is what lives further up the ladder this cloud is climbing, at the rungs Sunday almost certainly will not reach, but that the same sun, through the same mechanism, absolutely can. The answer is a short and sobering tour, because the gap between a G2 morning and the storms that put their names in history books is not a gap of kind. It is a gap of degree, and the degrees have already been used. Part 11. The Ladder Above. March 13th, 1989, 2:44 in the morning, Quebec. In the control rooms of one of North America's great power utilities, alarms began sounding, then multiplying, then cascading, and 90 seconds later, before any human operator could meaningfully intervene, the province's entire grid collapsed. 6 million people woke to darkness that held through a freezing morning and lasted for many 9 hours. The cause was not a hurricane, not an ice storm, not sabotage. It was a cloud from the sun, a coronal mass ejection that had left the star 2 days earlier and arrived carrying a large, sustained, southward-pointing magnetic field. That storm rated G5, the top of the ladder. Sunday's event is climbing, and this part exists to walk the rungs between here and there honestly, because the gap between a G2 morning and a night that shuts down a province is not a gap of kind. Every rung runs on the identical physics you now hold. A cloud arrives, its field turns southward, reconnection opens the door, currents surge, and the only variables are speed, field strength, and duration. The ladder is one mechanism at increasing volume. Climb it rung by rung. G3 strong, KP7. Aurora reaches the middle latitudes outright. Storm-level currents demand active management from grid operators. Satellite operations feel genuine drag and orientation disturbances, and high-frequency radio degrades across wide regions. Storms at this level happen many times per solar cycle, and most pass as spectacle plus overtime shifts. G4, severe, KP8, Aurora into the southern United States, widespread voltage control problems, some protective systems tripping hardware offline as a precaution, pipeline currents strong enough to interfere with corrosion monitoring, satellite navigation degraded for hours. The April 2023 storm that haunts this video's forecast reached this rung from an M-class start, and G5 Extreme KP9, the historic tier, where the catalogue stops being statistics and becomes named events with anniversaries. The 1989 storm is the modern benchmark for infrastructure, and its lesson is specific. The grid failure took 90 seconds. The warning horizon at the time for the field orientation that actually did the damage was effectively the same as today's, under an hour. Society's exposure has only deepened since. More long lines, more interdependency, more electronics per square metre of civilization, and we walked that exposure at length in our July 5th video on the power grid. So here we simply place the marker. The ladder's upper rungs are not hypothetical. They have been climbed within living memory over North America by an object of the same species as the one arriving this weekend. Climb higher, past the instrumental era, and you reach September 1st, 1859, the storm that carries Richard Carrington's name. A flare witnessed by eye through a projected telescope image, a crossing made in well under a day, and then a night in which the aurora burned so far equatorward that it was reported from the tropics, bright enough in places to read by. The world's only long-distance electrical technology, the telegraph, went haywire planet-wide, operators shocked at their keys, lines running on auroral current with their batteries disconnected, paper igniting in offices. The Carrington event is the calibration standard for the question every space weather agency quietly maintains. What happens if that arrives now? The sober published answers, from national academies and insurers, run to trillions of dollars and recovery times measured in months to years, driven above all by the vulnerability of the giant transformers that stitch continental grids together, hardware built over years and replaced over years. Between those bookends sits the storm sequence that modernized the profession's nerves, the Halloween storms of the late October and early November 2003. Over roughly 2 weeks, one hyperactive region fired off a barrage that included some of the strongest flares of the space age, and the resulting geomagnetic assault reached G5. The effects read like a systems engineering syllabus. A regional blackout struck southern Sweden when induced currents tripped a transformer. Airlines rerouted polar flights for days. Deep space missions registered anomalies. Earth-orbiting fleets logged failures and safe modes by the dozen. And one Japanese environmental satellite died outright. Astronauts took shelter in the most shielded module of their station, while the radiation storm outside climbed into the scale's upper tiers. And through all of it, aurora poured south night after night, visible from Mediterranean latitudes, a 2-week demonstration that the ladder's upper rungs are not single bad moments, but sieges. What made 2003 instructive rather than catastrophic was partly luck of orientation and timing. The worst eruptions were not all aimed our way, and partly the fact that the infrastructure of 2003 was measurably less interdependent than today's. Every subsequent vulnerability assessment has had to ask the uncomfortable question, not what did that storm do, but what would it do now to a civilization that has spent 2 more decades wiring itself together? And if your instinct is to file 1859 under distant history, the Sun has twice corrected that instinct within the current generation. In July of 2012, a Carrington-class eruption, arguably stronger, tore through the exact point in Earth's orbit that our planet had occupied 1 week earlier, a miss of 7 days in a game whose margins are usually measured in astronomical safety. We gave that near miss, and the deep time evidence of storms an order of magnitude larger still written in tree rings, its own full video on July 23rd, and we will not rewalk it here. And in May of 2024, the Sun delivered the real thing at reduced scale. The strongest geomagnetic storm in over 2 decades, a G5 driven by a volley of coronal mass ejections arriving in convoy. That storm painted aurora across essentially the entire United States, made casual photographers of millions, and, less charmingly, scrambled precision agriculture across the American Midwest at the height of planting season, self-driving tractors wandering off their satellite-guided lines as the ionosphere churned overhead. It cost satellite operators fuel and sleep, bent orbits fleet-wide, and passed without catastrophe, a full dress rehearsal that civilization substantially failed to notice it had attended. The May 2024 storm rewards 1 more minute, because its anatomy rhymes with this week in a way that should sharpen your attention. That G5 was not built by a single monstrous eruption. It was built by a convoy, a hyperactive region firing coronal mass ejection after coronal mass ejection over several days, the early clouds sweeping the lane, the later clouds catching up and merging, until what arrived at Earth was a compounded pile-up of ejecta arriving nearly together, their fields and sheaths stacked. Preconditioning plus persistence, the same 2 ingredients this video has flagged all along, scaled up. Now look at the past week through that lens. Multiple eruptions earthward across several days, watches issued and expired, a lane partially swept, and a fresh cloud in transit from a region still facing us. Nothing about that pattern predicts a repeat. The 2024 convoy was denser, faster, and driven by a far more violent region. But the template is the template, and it is why forecasters watch an active week differently than an active day. Single eruptions make storms, sequences make history. The aftermath of that storm also marked a small cultural shift worth noting. It acquired a name. Researchers took to calling it the Gannon Storm, for a beloved space weather scientist who had died suddenly just before it struck, and the christening said something about the field's trajectory. Hurricanes earned names when their impacts demanded public vocabulary. Geomagnetic storms are beginning to earn theirs, because their impacts are beginning to demand the same, and the storms capable of demanding it arrive, on average, more than once per decade. Somewhere in the Sun's future inventory is the storm whose name everyone will know. Here is the honest synthesis, and it is the sentence to carry out of this part. The Sun that sent Sunday's polite glancing G2 forecast cloud is the same Sun that sent 1989, 1859, 2012, and 2024 through the same mechanism, differing only in how hard the dice landed. Sunday is almost certainly a low rung, but you do not get to be a civilization that experiences the low rungs frequently without also being a civilization that will, on some unscheduled future weekend, meet a high one. The ladder is continuous. We live on it, which is exactly why the internet's relationship with events like this one is so poisonous and so worth dissecting. Because somewhere between the reasonable sentence, this mechanism has a catastrophic ceiling, and the unreasonable sentence, this weekend is the catastrophe, an entire online economy of dread makes its living. And this eruption, with its strange weak flare origin, and its officially modest forecast has already fed that economy a banquet. Part 12. The Doom Machine. Within hours of the halo appearing in the coronagraph frames, a parallel version of this event began propagating through social feeds, and if you spend any time in the spaces where space weather meets the algorithm, you already know its vocabulary. The eruption was enormous, and they are hiding it. The official forecast is a cover story. The flare class does not match the cloud, which proves the data is manipulated, and the perennial. This could be the internet apocalypse, the blackout, the big one, share, before it is too late. This channel exists in part because those claims deserve better than either amplification or a sneer. They deserve examination, one at a time, against the machinery you now understand. So take the 3 strongest versions seriously and see where each one lands. Claim 1, they are downplaying it. The suspicion writes itself, a government agency announces a big sun thing, and immediately assures everyone it will be moderate. Every disaster movie opens this way. But walk the actual information supply chain, the X-ray flux that graded the flare streams to the public in real time. The coronagraph frames that reveal the halo are published as they arrive. The proton counts, the solar wind numbers, the KP measurements, all of it flows outward continuously, unredacted, machine-readable, free, and it is precisely that public data that the Doom accounts screenshot for their content. The forecast is not a separate secret product. It is arithmetic performed openly on numbers everyone can check. For the downplay theory to work, the conspiracy would need to falsify the raw feeds themselves, coherently, across multiple satellites and dozens of independent ground observatories in many countries, in real time, without any of the thousands of academic and amateur users of that data noticing an inconsistency. Meanwhile, the genuinely uncertain part of the forecast, the best problem, the honest chance of overperformance, is stated openly in the technical discussions accompanying the watch. The system's actual sin is the opposite of concealment. It is that its honesty lives in prose few people read, while its confidence lives in a 2-character rating everyone does. Claim 2. A weak flare cannot make a big CME, so something does not add up. You are, at this point in the video, perhaps the best equipped audience on this platform to adjudicate that one. The claim's premise is the exact fallacy Part 4 dismantled. It assumes the flare class measures the eruption's total energy, when it measures only the peak brightness of a spike. The long-duration event is the documented, mechanistically understood, repeatedly observed category of eruption in which modest peaks lift enormous clouds, because the energy is spent over hours on mechanical work rather than in seconds on light. Far from being evidence of manipulation, the mismatch between this flare's class and this cloud's size is evidence that you are watching precisely the phenomenon the textbooks describe. The suspicious anomaly is a lecture demonstration. Claim 3, the Internet Apocalypse. This one is interesting because it has a real paper at the bottom of it. In 2021, a computer science researcher published a peer-reviewed analysis asking what a Carrington-class storm would do to global internet infrastructure. And its most cited finding concerned the undersea cables that carry intercontinental traffic. The cable's optical fibers are immune to induced currents, but the electronic repeaters spaced along them are potentially vulnerable, raising the spectre of continents digitally islanded for weeks. That is legitimate research about the extreme tail, the G5 ceiling, the 1859 scenario. The Internet Apocalypse content economy performs a simple, dishonest operation on it. It deletes the conditional. A finding about the worst storm in centuries gets stapled to whatever halo left the sun this week, and a G1 to G2 watch becomes a countdown to digital darkness. Measure the gap. Sunday's forecast sits 3 full rungs on a logarithmic ladder below the scenario the paper contemplates. The paper is worth knowing. Its deployment against every passing cloud is a category error monetized. It is worth being honest about why this genre works, because condescension explains nothing. The fear resonates for the same reason this channel's coverage resonates. The dependence is real. A century ago, a geomagnetic storm was a curiosity that bothered telegraph clerks. Today, the same event touches the electricity under every hospital, the timing signals under every financial network, the navigation under every ship, plane and tractor, and the satellites under essentially everything else. People sense correctly that modern life balances on systems they cannot see and do not control, and when a glowing ring appears around the blacked-out sun in an official image, that intuition goes looking for a narrative size to match the feeling. The doom accounts supply one. It is the wrong one, but it is emotionally proportionate, and debunks that ignore the proportionality convince nobody. The correct response to the feeling is not reassurance that nothing can go wrong. It is the calibrated truth this video has tried to deliver. Something can go wrong. Here is the measured ladder of how wrong. Here is where this weekend sits on it, near the bottom. And here is the genuinely thin place in our defences, the 1 hour B's horizon, which deserves your concern far more than any individual cloud does. For the practical-minded, the inoculation compresses to a habit you can apply in 30 seconds to any scary space weather post you ever encounter. Ask 3 questions. Who issued the number, an agency with a scale, or an account with a following? Which rung is actually named, and does the language around it match? Does the post say G2 but talk like G5? And is the decisive uncertainty acknowledged? Does the post know about Bs, or does it pretend the outcome is already fixed? Those 3 questions filter essentially all of the genre, because the genre's business model depends on you not asking them. Notice the pattern across all 3 claims, because it is the signature of the whole genre. Each one contains a true kernel, forecasts do carry uncertainty, the flare class is genuinely misleading, the extreme ceiling is genuinely catastrophic, wrapped in a false connective. Therefore this event, this weekend, hidden from you. The kernel earns the trust, the rapper spends it. And the tragedy is that the kernels, presented straight, are more interesting than the rappers. The truth that a civilization-altering storm is possible, and that our warning horizon for its decisive parameter is under 1 hour is more unsettling than any hidden CME fantasy, precisely because it is documented, quantified, and nobody is hiding it. The scandal is not concealment. The scandal is that it is all public and we mostly do not look. There is one more honest thing to say, and this channel owes it to you because we trade in dramatic skies too. Events like this weekend's are where trust gets built or burned for the real emergency. If audiences spend years being told every halo is the big one, then the storm that actually is will arrive to an audience trained to scroll past it. The boring discipline of matching language to measurement, G2 means G2, tail risk means tail risk, is not caution for its own sake. It is keeping the alarm bell credible for the night it must be believed. That is the ethic this video has tried to model, and it is why we can say, without contradiction, both of the following. Sunday is very probably a modest, beautiful, minor storm, and the mechanism delivering it deserves your permanent, calibrated, unpanicked attention. And because accountability should run both directions, put this channel's own cards on the table before the weekend does its judging. The claims this video has committed to are checkable within days. An arrival in or near the early Sunday window, a storm most likely in the G1 to G2 range, a real tale of overperformance if Bs arrive southward, a real possibility of anticlimax if the Grays passes wide, aurora plausible along the northern tier line if the peak verifies at night over North America. If Sunday delivers something outside that envelope, in either direction, the interesting question will not be who to blame but which input broke, the speed, the geometry, or the field. And we will cover the answer with the same specificity as the forecast because that is what separates analysis from content. The Doom machine never checks its own receipts. That, more than tone, is the difference between it and the people it parasitizes. So we return finally to the event itself, with one question left standing, the question that has shadowed every part of this video. The cloud is out there. The forecast is set. The Doom machine is humming. At 1 million miles upstream of this planet, a small collection of spacecraft is waiting to do the one thing nothing else in the human arsenal can do. Read the cloud's mind 1 hour before it matters. Part 13. The last 1 million miles. There is a place in space, about 1 million miles sunward of Earth, where gravity performs a convenient trick. A spacecraft parked there orbits the Sun in lockstep with Earth, the combined pull of star and planet holding it on station, like a buoy anchored upstream in a river. The place is called the First Lagrange Point, L1, and it is the single most valuable piece of real estate in space weather forecasting, because everything the Sun sends at Earth, Every gust of wind, every shock, every billion-ton cloud must sweep across that point minutes before it reaches us. At that buoy, right now, sit the Sentinels, the Discover spacecraft and its veteran backup ace, which has been on station since the late 1990s. Their instruments taste the solar wind directly, the actual particles, the actual magnetic field, not an image or an inference, but the medium itself, and they radio the measurements home at the speed of light. The arithmetic of the arrangement is beautifully stark. The cloud crosses L1 moving at hundreds of kilometers per second and takes tens of minutes to cover the final 1,000,000 miles. Its radio-borne measurements cross the same distance in 5 seconds. The difference between those crossing times is the total advance warning Earth gets on the one question everything else in this video has been forced to leave open. For a slow cloud, about an hour. For a fast one, closer to 15 or 20 minutes. Sometime late Saturday night into Sunday morning, if the forecast holds, the buoy rings. The traces from L1 flat all week will jump in a single minute. Wind speed stepping up from 300 and change to 5, 6, 700 kilometers per second. Density spiking as the ploughed-up sheath sweeps past. Total field strength doubling or tripling. That is the shock, and its signature is unambiguous against this week's dead calm baseline. And then, with the whole planet's forecasting apparatus staring at one wiggling line, the real reveal begins. B. The north-south needle. The rope's secret, held since Thursday, finally read out in plain numbers. If the trace dives southward and holds there, -10, -15 nanotesla, hour after hour as the flux rope's coil winds past, the door opens and the watch verifies or overperforms, and somewhere over the dark side of the planet the sky begins to move. If the trace floats northward, the door stays shut, the cloud slides around the magnetosphere like water around a stone, and the great event of the weekend becomes a footnote with beautiful upstream data. One line on one chart, updated every minute, watched by every forecaster, every grid operator on alert, every aurora chaser with coffee and a northern horizon. It is the closest thing modern civilization has to opening the envelope. The width of that warning window is not fixed, and the reason is worth one beat of attention, because it contains a small cruelty of physics. The window equals the cloud's travel time across the final 1,000,000 miles, which means the window shrinks exactly when you need it most. A gentle, slow cloud grants a leisurely hour between the buoy and the door. A monster moving at 2,000 kilometers per second, the class of object that built the historic storms, crosses the same distance in under 15 minutes. The more dangerous the storm, the less time its warning buys. Grid operators know this arithmetic intimately. It is why serious geomagnetic contingency procedures are designed to execute in minutes, and why the research community keeps pushing for instruments that could read a cloud's field orientation remotely, mid-transit, days out. Until someone solves that problem, and no one has, the L1 buoy line is the entire difference between forecast and ambush, for every storm at every scale. Know also what the watchers will do if the appointed window passes empty. Nothing dramatic. Arrival forecasts miss by 6 and 12 hours routinely, and a Sunday morning that dawns quiet does not falsify the cloud, it retimes it. The watch gets extended, the models get rerun with the null result folded in, and the desks keep their vigil into Sunday night, because a late cloud and a missing cloud look identical until the moment they stop looking identical. Only after a day or more of continued silence would the verdict shift toward the anticlimax that is always quietly on the table, with a glancing blow geometry. That the shoulder passed wide, the flank never touched us, and the whole apparatus of this weekend stood watch over a miss. That too would be recorded, verified and fed to the models. In this business, even the storms that never arrive improve the forecast for the ones that will. It is worth sitting for a moment with how strange and how recent this arrangement is. For all of human history until the space age, a geomagnetic storm announced itself by happening. The 1859 operators learned of their storm from the sparks. The 1989 operators got it from the alarms 90 seconds ahead of collapse. Today, a species that cannot yet predict its star's eruptions has, through 4 decades of quiet engineering, purchased itself a guaranteed window, brief but real, between knowing and experiencing, enough time to reconfigure a grid's loading, to safe a satellite, to wake a control room, to step outside and look north. The window is under an hour, and everything in this video conspires to make you feel how thin that is. But do not miss the other half of the truth. That hour did not exist within your grandparents' lifetime. It exists because instruments were built and parked 1,000,000 miles upstream on the theory that someday, on some weekend exactly like this one, minutes would matter. And after the front passes, whatever it brings, the accounting begins. Verification is the unglamorous backbone of forecasting. Did the arrival land inside the window? Did the peak match the 5.67? Did the gray's geometry hold? And every answer feeds the models that will time the next cloud better. The proton curve gets its coda too, whether Friday's threshold flickering warning expired at midnight uneventfully or surged again when the shock swept past. The closing data point in the story of the storm that could not decide whether it existed. All weekend, the numbers will be settling into the permanent record of an event that began with a flair too modest for anyone's front page. That record has an audience beyond the forecast desks, and it is worth knowing who reads it. Every well-measured arrival becomes a data point in the research literature on CME propagation, drag, and deformation, the very physics whose uncertainties this video has catalogued. Events like this one, moderate, clean, caught by a new operational coronagraph from launch to landfall against a flat baseline, are disproportionately valuable, precisely because nothing else is muddying the signal. Years from now, when the arrival time error bars on some future stormwatch are a little narrower than this weekend's, a small share of the improvement will trace back to whatever happened Sunday morning, folded into the statistics. The storms teach us to time the storms. It is the slowest feedback loop in meteorology, one lesson per eruption, and it only advances when the sun assigns homework. But the sun does not wait for our paperwork, and here is the fact to carry past the weekend. Active region 4492 is still there. The spot group that spent hours patiently lifting this cloud is still crossing the Earth-facing disk, still carrying its twisted fields, still, for the next several days, aimed at us in the way that matters. Regions that produce one long-duration eruption are regions that have demonstrated the specific talent this video has been anatomizing, the slow, deep release that moves real mass, and the week ahead belongs to that region's temperament. Perhaps it is spent. Perhaps Thursday was a throat clearing. The filament channels around it will reload, the flux will keep emerging or decay, and the only certainty is that the region's next decision, like this one, will be graded first by a number that lies and understood only later by the machines that watch. So here is where you leave this story, and where this story, for the next 30-odd hours, leaves everyone, from the duty forecaster to the farmer with the auto-steered tractor to you. 1 billion tons of a star is crossing the last stretch of dark toward a planet that has measured everything about it, except the only thing that decides the outcome. We built the cameras that watched it leave. We built the models that timed its crossing. We built a buoy 1,000,000 miles upstream to read its secret with an hour to spare. And still, on the night it arrives, the most advanced civilization this planet has produced will be doing exactly what its ancestors did under the red skies of 1859, watching, waiting, and finding out in real time. The cloud knows which way its field is pointing. It has known since Thursday. The question it has carried across 93 million miles of empty space. The question no instrument on Earth can answer even 1 hour early is the question Sunday morning will answer for everyone at once. When the rope uncoils against our magnetic field, which way will it turn?